I think we are going live. Hello, everybody. Hello, Ben.
Hello.
How are you doing?
Very
Hello,
well.
David.
Hello.
Welcome back, David.
Yeah.
Usagi Electric.
Thank you. Yeah, I got an invite back. That means I did all right on the first one, I guess.
Well, us dinosaurs were going to talk about tubes, and so we thought of you. So
awesome. I'm flattered. Thank you.
Actually, I thought of your bunny first and then you, but that's
I mean, the entire YouTube channel exists so that I can post videos of the bunny.
Of the bunny and not be thought to be a dangerous element in society. Yeah. Excellent. So no, we really are talking tubes today, and you just happen to have come out with a video about your video computer, tube-based computer in the last week, right?
It's a beautiful thing.
It's growing. Now that I have space for it, I'm working on it again. I was having trouble with where to put it. Like it requires essentially an entire wall, and so I had to build a wall to dedicate to it.
That's so good. Hey, there's more space yet behind you to add new instructions.
Yeah. So directly behind me, there's actually a little piece here for expansion boards that are going to go here. So ultimately, there's going to be 4 of these that are that size.
And how much current will it take by when you're done, do you think? Do you need more than one 15-amp breaker? How's that?
Probably. I did some back of the napkin calculations, and I think we were saying that it was like a little over a kilowatt or something like that. So it's a decent chunk of power. Probably on the 24-volt line, we're probably looking at maybe like 40 amps or something like that.
Okay.
Wow. And then the heaters, just the heaters alone are.
That's all heaters. Everything's here. I don't even calculate the B plus. I mean, the B plus voltage is 24 volts, but I don't even calculate it because we're talking it's like in milliamps.
Right.
So everything is in the heaters.
Yep.
Right. Yep. Right. And for those that don't know, heaters are the thing you see when you turn on a tube. It's that purely I don't want to say a waste of energy, because some electrons come off, but most of it comes out in the form of heat and light, from the old days. And I was thinking back to the first tube radio I ever kind of tore apart. And back then you would put all the heaters in series so that they added up to 120 volts. So if I remember right, there might have even been like a 35 something, because not every tube was a 6-volt tube.
That reminds me, Bill, too, like there's some classic guitar amps, tube guitar amps, I think by Ward's Airline or Sears Silvertone, some older ones I have in this book, right? This is you can't get this book anymore, and no, I'm not going to ever sell it.
It's good for us.
But there are amps in here that take their power straight from mains. They used to do that.
I've got an old Philco radio that does that. It doesn't even have an isolation transformer. You just have mains coming straight into the rectifier.
Yep. And I used to get shocked off the chassis if you got that plug in wrong, because the plug was reversible, even though it was one blade was slightly bigger than the other.
A little bit fatter. That's it.
Yeah. We used to, I was always, taste testing everything before I worked on it.
That's actually why a lot of those old radios, like the Philco I have, the cabinet is all wood, and the buttons are like Bakelite. It's all non-conductive stuff. So everything that's like customer or user facing is non-conductive.
Right.
So you can have a totally hot chassis inside of this, to where if you touch something, it shocks you. But on the outside, what the customer will normally touch shouldn't ever shock them.
And even some classic amps from as late as the late 60s or mid 60s, like the Fender Blackface amps have they originally were made without a ground pin, because back then most houses didn't have ground pins in America.
Right.
That was totally Britain, Australia, Europe always has had ground pins for many decades because of the safety thing, right? But you have this big metal chassis in the back of the amp, and the front panel, it's all metal. And the neutral in the house or the building you were playing in was wired neutral to the ground, maybe at a central point in the building, but you'd get all this hum, right?
Right.
And so and because the plug was just a 2-prong and reversible, you didn't know which was neutral. So they have a switch on the back of the amp chassis that links a 0.047 microfarad capacitor, and it chooses which of the 2 power conductors coming into the amp is shorted to chassis through the cap. So you have this reactive link, and and this was the problem with PAs, right? The singer would be there with a guitar, electric guitar, hands on the strings. You're grounded all the way through to the chassis of your amp, but the chassis might be switched through the capacitor to the height. And as soon as your lips touch the microphone, it's like, because your lips are wet.
Wakes you up.
Beer is a great conductor, by the way.
Right. And it's not like your fingers aren't on metal guitar strings or something else equally conductive. Yeah.
So, yeah.
That's why we only have 120 volts. It's just enough to piss you off, but not enough to kill you.
Well, it's through the cap. So it's dropped reactively, but it hurts. So, yeah.
Yeah, no, I grew up afraid to death of 230 volt, but like you said, 115, I got hit enough that it was mostly about getting pissed off that you got hit rather than.
I had a little tube amp that was, it was a little spot monitor that came from it was getting thrown out from my oldest brother, who was 14 years older than me and taught me electronics. He was a electronics tech, and he worked for the Australian Broadcasting Commission, the big TV studio in Sydney, and they were throwing out old gear. So he brought home this little amplifier with a little 6-inch speaker in it. That was one of those things that used to be bolted onto the wall, and it was a death trap amp. It had a metal folded chassis in the back that normally, because it was on the wall, you couldn't get to it, and it just had an input, and the speaker was built in. And I used that as one of my first guitar amps when I was a teenager. And I just put my hand in the back and got 240.
Oh, wow.
Ooh, that'll wake you up.
It really hurts. It really hurts. 240 hurts like you wouldn't believe.
When I was working on my HP 150A oscilloscope, which is an all vacuum tube oscilloscope, weighs, I don't know, about 120 pounds. I throw my back out every time I pick it up. But when I was working on it, I was trying to figure out what was going on. So I had the case off of it, and I would lay it on its side, and then I'd check some stuff, and I'd put it back on its top. And I would always make sure to turn it off in between when I would, move it around. But I would always forget to unplug it from the wall. So when I was moving it, I would just reach around and grab the back side of the power plug, which has live AC on it.
Yep.
And I did that about 10 times, and that was when I realized that A, I'm kind of dumb, but B, 120 won't kill you.
120 is a lot safer than 230, I'll tell you that.
Right. Now, Ben, did you grow up calling them valves?
Yes, I did. Everywhere outside of the United States that I've been in the world, they're called valves.
See, and we thought you guys were just doing that to be different. We're like, they're really tubes, you know?
It's official. Yep. It's official. They're called valves by the manufacturers.
It depends on which manufacturer, though, because I have some tubes that say electron tube on them.
Tube. Yeah. I remember the RCA boxes. I used to have tons of those little red and white RCA boxes.
This is very precious to me. That one doesn't say tube. I don't know if I can get that to focus. This is my private stock I inherited from my brother when he passed away.
Mullard is an excellent company. They make good tubes.
And they made them in every local market. So these tubes were actually made in Sydney.
Wow. All right.
They had a factory, AWA also, they had branding deals. And some of them are branded AWA, Amalgamated Wireless Australasia. Right. AWV was their valve making branch of that company, which was partly government owned. But there were factories for this in Australia.
Right.
And all that's long gone. And so these are very precious to me. But anyway.
So the reason I moved out of Central America from Indiana to Pennsylvania was my dad was working at a picture tube plant, so a big electron tube. And so I grew up knowing what heaters were and cathodes and that kind of stuff. But it literally, you mentioned tubes in Australia. There were no tubes in Indiana. We had to move to get around enough industry to support tubes when I was growing up.
So these ones, these are called tubes because Mesa, of course, is a California company. These aren't the actual Mesas in the box, unfortunately. These are the ones that were replaced by the Mesas that were in this box back in the 90s when these were purchased. But these were still made in America at that time. Or maybe they were made, maybe these were Russian and rebranded, but I thought there was still, yeah, these are tongue soles, so these are Chinese or Russian. Wow. But yeah, so Bill, for those who are too young to know, we sometimes have young people. Can you give us a rundown on tubes?
No. Tubes were around before we figured out semiconductors, right? And we needed some way to turn stuff on and off. And I believe they first figured out you could put gas in a vacuum and it'd light up, and that's where neon came from and stuff. But they then set out to make a better vacuum. And they found when they did a better vacuum that they could control this mystical force. It's before they understood why electricity worked. They were manipulating electricity. And that to me is the tube generation. And then they got better and better at it, added control grids. But basically you set up a high potential between, and you have to use a heater on the cathode to emit electrons, to heat it up so that a thermonic emission of electrons. And then you put something in the middle called a control grid that turns it on and off.
So
and
basically, they are a field effect device, essentially. They didn't call them that back then. That term didn't come in until the field effect transistor was developed, which does the same thing, but in solid state, in a silicon platform, whereas a vacuum tube does it under vacuum. So you have metal, and electrons are kind of free in metal. That's why metal conducts, but they won't jump out of it unless you do something really hard to make them want to leave.
The interesting story that I read about that, because what you're talking about is thermionic emission, the idea
exactly.
that
so you heat the metal up, they lose. Yeah.
So whether how true this is or how well I remember it, I'm not sure, but the story that I remember reading was that they had light bulbs was where it came from. They had their AC going into light bulbs, but or DC going into a light bulb, and they noticed that one electrode was getting darker, and the glass was getting discolored around that electrode, and they couldn't figure out why only one was getting darker and not the other. So they were trying to improve the quality of their light bulbs when they discovered this concept that if you get the filament hot enough, it slings off electrons. And so what was happening is the filament was getting hot, the electrons were floating, and they were going to the closest potential they could find, which was the other electrode of the filament there. And so then they went, so they went, okay, well, if we're throwing off electrons, if we put a different plate in there and give it the positive potential that the electrons want, instead of the electrons going to the only place that they can, they'll go to that positive potential.
And so diode was invented.
That was the diode. And then it went on to Lee DeForest, I think. He made the first triode, or at least I think he's credited with making the first triode, and he made the Audion tube.
How about the brilliance of that? It's like, okay, well, maybe I can actually create a valve and control the flow from the filament to the plate, and do that using a grid or a screen of wire that's spaced apart, but it pinches off the flow of electrons as you bias it more and more negative, because it's creating a like charge, so it repels the other electrons or gradually closes off all the little holes they can fly through. And it's and if you keep going more positive, it can add more to it as well. and add acceleration to them. And it's just amazing that people can learn just enough about something and then think of the next thing.
It's all about how can we use it. By the way, for my audio, I tried turning off echo cancellation. It might still sound too hot, but I'll keep tinkering with it and see if it gets better. So anybody's watching, if it still sounds funny.
Further down again, it would be it's AGC's kind of like
clipping. It's just clipping a little. It's not too bad.
Right at the beginning. So and Chris called it the Edison effect that you were describing with the one with the sputtering of the material and everything, I believe.
I do recall reading that whole story in a Dick Smith Funway 2 book, the Green Book. I think Dave Jones has explained what those are many years ago in his channel. This is how most of us in our age group got started in electronics when we were kids.
Yeah.
They used to have the kits. Like in America, you would have Heathkit and there'd be hobby electronics magazines. We had our own versions of those in Australia. And the Dick Smith Funway series, the second book, explained Edison's that whole story. Edison inventing the light bulb, and then other people working for him trying to solve that problem and discovering the diode, and then that led to the triode, and then of course the rest is history. But end of World War II, the transistor comes along. What was it, 1949, the first transistor? I think it was 1949 if I recall. But anyway, so
it was early enough that it took vacuum tube computers were still prolific for like another 15 years after the invention of the transistor or something like that.
Well, and that also makes sense too, because it probably took 15 years for transistors to become reliable enough for computing applications.
Yeah. And the first transistor, the model of it is fascinating because it's like a wedge on a spring with like two different materials taped to one side, pushed against like an actual chunk of rock.
Yeah. Yes. 47. Thank you, Chris. Yeah.
Yeah, 47. Yeah.
I
So
right around that time.
In 47, that was like, if we're talking about computers, that was like still in the days of the ENIAC. And the Colossus, I guess the Colossus had been destroyed by that time because it got destroyed just after the war. But yeah, we had ENIAC, and I think IBM was just getting into it. By the time they got into the mid 50s, they were using germanium diodes a lot, but they hadn't quite gotten up to transistors just yet.
I'm just going to open an image in a tab here, just that kind of helps describe what we were just talking about. But this is a classic picture from there's a few of them actually from RCA's tube manuals back in the day. Let's see, I need to go back to that tab. but just briefly, because we want to get into what you've been building here as well. But so this is what I'm talking about.
That's from the IBM 604 manual.
And this turns up in just about every kind of tube book you could get that's from the era, but it comes originally from the RCA data book. And
okay. The IBM 604, they drew one that was very similar, but I think that one's showing what they call
this is a beam power pentode.
Yeah, beam power pentode.
So the 6L6 is still probably the second most widely used tube in guitar and hi-fi audio amps even today. It is still one of the ones that's still manufactured in Czech Republic, Russia, and China. Not Czech Republic, Slovak Republic, I think, is where JJ's factory is. But yeah, this is a beautiful image because it really helps intuitively understand how tubes work in general anyway. You've got these electron streams because of the plate is a positive voltage and the cathode is at ground potential, let's say, or closer to ground it's more negative compared to the plate. And inside that cathode is a heater that heats up the metal and makes the electrons all loose and want to jump off in a cloud. But they have to squeeze between the control grids, which are just these thin spirals of very thin wire, typically, nickel or some kind of plated alloy. And if you put the control grids more negative, they pinch off the flow of electrons because they have a like charge. So they want to repel those electrons. So it's like closing off the stream. And that's how the whole thing works. So.
And what's really interesting, you're showing a beam pentode here, but a lot of other tubes, like regular old pentodes, they have an actual suppressor grid themselves. But the only
Can you
grid
make the picture bigger?
I'm trying.
Yeah.
Oh, there it goes.
There it goes. Yeah. So this one is showing the cathode, the control grid, and the screen grid, but there's no actual pentode grid in this picture, and that's because it's using a beam forming plate to essentially create a suppressor grid out of floating electrons. But a lot of other pentodes actually have another physical grid that is a suppressor grid instead of forming a beam. But the only grid in there that is controlling the flow of electrons is just the control grid, the one right around the cathode. Yeah, the innermost one. And if you look inside an actual tube,
the screen grid is actually tied to it's tied together with something else inside the envelope. I forget which. Or
so usually you pull the screen grid high, you pull it up to your B+ voltage, and you pull the suppressor grid low, you pull it down to your cathode voltage.
Mm-hmm.
So man, I'm not great with audio applications here because being deaf in one ear has kept my interest in them slightly low. But for computer purposes, the screen grid works excellently as an electron accelerator. So the control grid is essentially squeezing off the flow of electrons. But when you open up that control grid, the screen grid is a lot closer physically to the cathode. So it will give the electrons some massive, strong attraction.
Wow, did we lose two people?
No, I'm here.
Okay.
Okay. Hopefully he comes back in a sec. That's disappointing because what he was saying was really, really cool.
So, Ben, I was looking for usually this is about the time where I wave around my RCA tube manual and I can't find it. That's why I've been kind of disappearing here, looking around for my old blue and white. But you're right. That picture I just grew up with that picture you just showed. And, they were talking about beam forming. I remember hearing when I was young that's how they got it to be a linear type of transfer function, the shape of the beam forming plates and whatnot.
Right. Yeah, because the actual, if you do curve, if you what's it called? If you do curve tracing of the devices, basic triodes and diodes have very nonlinear characteristics,
right?
Which is also what gives them the thing that guitarists like, which is distortion, right?
Right.
But it's a very smooth, easy-going distortion. The beam pentodes were particularly favored for power amplifiers because of the linearity that it gave you.
Right.
Exactly.
And I just remember I was a big 6BQ5. Now I've forgotten. You get old enough and finally the errors start.
6BQ5 is the American designation of
6.
Oh, that's an AQ5, which is not the same. But the BQ5 was the American designation for an EL84, which is also used in a lot of audio power amps. He's back.
Yes.
I'm back. My Wi-Fi out here got too hot. Apparently, we were talking about tubes a little too loudly.
Well, Well, you were talking about something really interesting. Do you remember where you were when you?
Let's see. We were talking about control grids and screen grids.
Right.
Screen grids
And
acting as
active
electron
accelerators.
accelerators.
Yeah.
Yeah. So the screen grid provides a really strong attractive force for the electrons boiling off of the cathode. But the electrons just blast right by it because the screen grid is too sparsely wound and there's not enough surface area there. Sure, some electrons collect on it, and that's why you often need a screen grid resistor, so that way you don't have too much current flowing through the screen grid, but most of them fly right by it. And then the suppressor grid, if we're not talking about like a beam pentode there, if we're talking about one that is an actual grid, it's really sparsely wound. So the electrons don't even know it exists. And then they strike the plate because that's where they want to be. They want to be with their opposites attract. And when they hit the plate, sometimes they hit with such a force that they knock other electrons off. Right. This is called secondary emission. And that's what the suppressor grid does, because the second electrons that get knocked off are moving a lot slower. I'm sure the physics of it is a lot different, and the smart physics people are going to tell me that I've got something slightly wrong here. But the electrons coming off have a lot less energy, and again, like charged particles repel each other. So with the suppressor grid being at a negative potential, that electron kind of comes off and goes, no, we don't want that, and it goes back over to the plate. So the plate can gobble the electrons that get knocked off back up again.
Right. Right.
Now, what's interesting is to tie all of this into this jobby behind me is that I actually use pentodes for everything. I'm using 6AU6s here, which raises a good question of why didn't I use triodes?
Triodes.
Right. The obvious easy answer is that triodes were expensive and pentodes were cheap. But there's also, like, I did a lot of testing, and triodes behave very differently when you're trying to do what I do here, which is either push the tube all the way to cutoff or pull it all the way into saturation. Ben, as I'm sure you're aware, that when you're dealing with audio, if you hit cutoff or if you hit saturation, you're clipping, right? And so the audio signal goes to trash. So triodes are fantastic because they have a wonderful linear region in between those two extremes. But for this, I'm doing the exact opposite. You want a
hard on, hard off in digital.
Exactly. Right. That's right. I want to go full saturation or full cutoff. I want to do one extreme or the other. Yep. And you run into an interesting problem if you don't have a screen grid, like if you just have a triode, because a triode is just a cathode, one grid, one plate, that's it. Tri being 3, you've got 3 active elements in there. And that is that when the electrons fly off of the cathode and they strike the plate, you usually have a plate resistor up there, and then you're pulling your output directly off of the plate, right? So if the control grid is off, no electrons are flowing up to the plate, and so your plate resistor there, your anode resistor, pulls the value of the plate up to your B plus value. If your B plus is 100 volts, pulls the value of your plate up to 100 volts. But if I push the tube all the way into saturation, essentially I'm trying to connect that plate to the cathode.
Right.
And I'm doing that with a stream of electrons, right? But the lower the potential of that plate becomes, the less attractive force it has for the electrons. So you hit this equilibrium where you can't actually pull the plate any lower, because if it does get lower, the potential is too low and the electrons are no longer attracted to it. And so that's where the screen grid really helps. It provides this strong, because the screen grid never comes low, it's just tied to B+. It provides this strong electron accelerator force that rips those electrons off of the cathode, and then they don't have anywhere else to go except for the plate. So I'm running incredibly low B+ voltages here. I've got just 24 volts for my B+. And this exacerbates that problem ridiculously because the margins are so much tighter. If you have 200 volts on your B+ and your saturation voltage is 50 volts versus 60 volts, whatever, right? But if my saturation voltage is 5 volts versus 10 volts, that's a huge difference, and my logic circuits no longer work correctly. So I was finding that with triodes, unless it's a 6DJ8, for some reason the 6DJ8 just blows everything else out of the water. But pretty much every other triode that I tested, 12AX7, 12AU7, every one that I had, 6BQ7, the logic low would only come down to about 8 volts, whereas on the 6AU6 I could get the logic low all the way down to 2 volts or 1.8 volts or something like that. So the screen grid makes a huge difference there, acting as that electron accelerator.
Well, how many tubes did you try? I didn't realize that you had done so much experimentation down at the nuts and bolts level there.
I tried just at that time, this was about 2 years ago, but I tried just about every tube that I had in my collection. So I don't know, probably on the order of 50 or so different types of tubes.
Wow. Wow.
Yeah, and I would what I would do is I would just set up a little circuit that had like a 33K plate resistor and then a little potentiometer on the grid, and then I would tie the cathode to ground, and I would set the grid at -5 volts and write down what the plate voltage was, and set it at -4 and write it down. Yeah, I just did it down and put it all into a just put it all into an Excel sheet.
I'm surprised you didn't. I'm surprised you didn't adapt. There's a few open source curve tracing projects out there. There's one I was looking at the other day using Arduino.
It might have been mine. I made one.
Oh, you did? Oh, you did do that. Okay. Right.
Eventually I did, after I got tired of doing it manually.
Yeah, because it's going to take some time.
Yeah.
Yeah, remember the days when you could go to the local drugstore and there was a tube tester there and they would kind of try and do simple tests? A lot of them were just heater, where they were heater testers, but some were actual emission, testers.
Yeah, they do. It's like I think the way that those work is that there's no plate resistors or anything. They just put a big voltage on the plate, pull the grid high, and see how much current flows through it or something like that. They have a little ammeter in there, but you don't get any data. It's just like the needle moves and you just got a section that says good and a section that says bad.
Yeah. All the tube testers I see on eBay are like that. It's like, no, I want a full on e-tracer, but they're, even as a kit, they're quite expensive. Can't really justify it right now, but at some point I will.
Yeah, the one that I built that was based around the Arduino had a large plate resistor. It has a 33K plate resistor, and I'm checking at that because it matches what I'm doing here. So it was a tube tester specifically designed for this. But I was working on another one that was low side testing, where it tests the current across like a 10 ohm resistor on the cathode. To answer Chris's question there, they're not new old stock. They're all used. Every tube that I have is used. I have all the tubes that I use on this are 6AU6s. That's my favorite tube. I've got like 1,400 of them. They made a lot of vacuum tubes, and they're all still out there. They're just not in the traditional places that you would often look for them.
You need to go to ham swap meets if you want to get any kind of tube. You can find them at ham swap meets, and you'll probably find the bizarre ones that you don't find in guitar amps.
Yeah,
you'll find a lot of other stuff like fast
the 686.
Yeah, like 6
or 6CB6 or if you're not looking for the highly sought after audio tubes, so like a 12AX7 is very popular. The 6SN7 is really, those tend to command high prices. If you just want to have like a tube to red plate or play around with, or crack open and see what's inside of it, just get some old TV tubes. You can find like 3 CB6s and stuff like that. Usually if you start talking to the right people, i.e. me, I have hundreds of tubes that I'm never going to do anything with. They'll just give them to you for free, because oftentimes, I know, oftentimes we buy a big lot of unknown tubes because we're looking for specific ones. And so it's just, somebody had a box of tubes that has like 600 tubes in it and they didn't want to sort it. So me and other crazy people like me will buy that box and we'll go through and sort it all out. And we go, these I like, these I don't care about. And then because we're hoarders, we don't throw anything away. We just put them into a box somewhere. So if you go find some ham guys or some vacuum tube aficionados, they often have a couple thousand tubes up in the rafters somewhere that they just they haven't touched in years.
So tell us about that thing behind you then. We've been talking about the tubes, but that big, it's
the
hard to
computer.
see, but that's a bunch of tubes behind
The tube
right?
computer. We'll see if I can pan it down a little bit here to get the whole thing in shot. So this is the beginnings of a vacuum tube computer. It's not a very powerful or good vacuum tube computer, but it's my vacuum tube computer, and I love it.
And it's a beautiful piece of art, I must say. It looked awesome on the wall there, and
yeah, it's finally got a place. I haven't done anything with it all summer because I haven't had a good place to put it because it's growing too fast. Like, it's getting too big to keep inside, and so I've built this new room that I have here. That is my dedicated electronics room, and so finally I made sure that I had a wall that I could dedicate to this machine, so I'm starting to get back into working on it. The boards you see here are just a random arbitrary size. So the whole project started with me wanting to build a vacuum tube computer, but realizing that something like an 8-bit SAP1 or whatever, 6502, if you want to do a 6502 out of tubes, you go like, oh, okay, I need 10,000 vacuum tubes to do this. That's a problem, right? So I got obsessed with this chip called an MC14500. It's a little Motorola 1-bit industrial control unit meant to replace relay ladder logic in industrial situations. So they often used it for like stoplight controllers or the turnstiles at like subway stations and stuff like that. Those are just state machines. It's technically a computer, but it's really only dealing with 1 bit of input to give 1 bit of output. And I modified it a little bit because the MC, the Motorola chip, only had a logic unit within it, and I wanted an arithmetic logic unit. I wanted to be able to do addition and subtraction. So I rebuilt the ALU in it, threw in a carry register, and that's what this top half is here. So this is the entire computer. You have a 4-bit instruction register up here. It's hilarious to actually be able to point at bits of a processor.
Yes, it is.
And that goes through a decoder that breaks it out into the 16 control lines for the different instructions. Those all get buffered, come down through here. We have an input enable register, so this controls whether data is allowed to come through the data bus into the ALU. Then we have our subtraction exclusive order unit here. This is for doing 2's complement, I think. And then when we get down here, we have the logic unit and the arithmetic unit. It's 2 separate things, so a total of 16 tubes for that. And then we have the result register and the carry register. So the result register stores the result of whatever operation we just did. And if it was an addition or subtraction operation, we get a carry bit out of that operation as well. So we store that in the carry register up here. And then again, it comes over to the bus. We have an output enable register down here that controls whether whatever we have in the result register is allowed to make it to the memory to store. And then we've got essentially a bunch of buffers and stuff to get information out of the processor. And then that's going to come down to this bit that's down here ultimately, and this is the memory. So this big string of tubes up on the top here actually use some dual triodes up here for buffering. But this is all just kind of addressing control. So we have a 6-bit memory address to select individual bits. Since I'm storing 1 bit at a time, I don't get very much memory with the 6-bit address. But we take that and we put it into the memory down here. Now I've only got 4 of these. You can see how there's 4 distinct boards going on here. I've only got 4 of these built. Each one of these boards is 1 nibble of memory. So 4 bits of memory. So this right here is two whole bytes. 2 bytes of memory.
Right.
16 bits. And ultimately that's going to expand out to 6 bytes. So we'll have 6 bytes of vacuum tube memory here that we can store and select and do stuff like that.
And it's true static memory, as in you're using flip-flops. synchronous?
Yes,
flip-flop?
absolutely. So it is it's just straight up a D flip flop. I actually have I have one little bit right here that I can show you guys. So this was my first test piece here. So this is what 1 bit of memory looks like. So it's four 6AU6s, one 6977 vacuum fluorescent display. Now, the right way to have done memory on a vacuum tube computer would have been the way that everybody else did it, which was like core memory or a rotating drum.
Yep.
I didn't do that because
You don't feel like knitting.
yeah. Well, the thing about core memory is that if you're just building a very small amount of memory, it's not worth it because the amount of control circuitry that is required for core memory would rival the number of tubes required to just make that amount of memory out of tubes. But core memory scales extremely well. So if I wanted like a kilobyte of memory instead of just a byte of memory, core memory would have been the answer.
Right.
But
in which case you'd have a honeycomb basically of little frames with
and then X line drivers and Y line drivers and sense amplifiers and I mean it scales pretty quickly. Like I did some rough looking at IBM's core memory for the 650 or the 705 maybe, one of their vacuum tube computers, and just glancing through the schematics and looking at pictures of it, just the control circuitry for their core memory was over 1,000 tubes. And so I was like, but I mean, if you wanted, they had a lot of memory, and if you wanted that much memory out of pure vacuum tubes, it would have been over 10,000 tubes. So it scales really well. But the one that I'm using here is it's like a static RAM cell essentially. It's just a simple NOR gate only D flip flop here. And so I'll see if I can share my screen here. Let's go share screen. All right, can you guys see that?
Yep.
Yes.
All right, so this is the schematic for one memory cell, and it's actually it's just a simple D flip flop. But what makes it really interesting is that I'm using a combination for the flip flop, and a D flip flop, if we're being honest, is just an SR flip flop with a little extra gubbins on one side of it. So an SR flip-flop is as simple of a memory cell as you can get. It's essentially just two inverters feeding into each other, and then you overpower one or the other. I'm building the SR flip-flop with a mismatched 6AU6 and 6977, which is kind of a ridiculous idea, and one that would normally not be possible because a 6977 is a vacuum fluorescent display, which at the end of the day is a vacuum tube triode.
It is. And actually, even recently, the company Korg from Japan, the synth company,
they created
maybe
the new
5
tube.
years ago, came out with this, a twin triode called the new tube that was just made from their VFD plant. I guess someone's like, you know what, there's something else we could do with this and it would make money.
Yeah, exactly. And, all I'm doing is, I looked at that and I went, all right, so a 6977 is a triode. I could use that as one half of my SR flip-flop and a visual indicator. So that way I can see if a bit has been stored or hasn't been stored. And it took some finagling of resistor values and a lot of trial and error, but I actually got to a point where it was flipping and flopping with the 6AU6. And then I take the actual output off the plate of the 6AU6 and it goes through another amplifier on its own. So the actual output value is a properly amplified signal, but the part that stores the actual bit of information is the 6977 and the 6AU6. Now I could have easily done this with two 6977s as well, but 6977s are jolly expensive and 6AU6s are cheap. So I wanted to use only one of them if possible. And so this is what I find fascinating about this is that it's something that is not possible unless you're crazy enough to try and run a 6AU6 at 24 volts. because the VFDs are inherently low voltage. So the 6977 has a max voltage of 30 volts on the anode, whereas the 6AU6 is often expecting 100 to 150, right? But because I'm doing this ridiculous idea of building the entire vacuum tube computer with only 24 volts as the B+, it opened up this interesting avenue where I could combine this 6AU6 and a 6977 in this mismatched, uneven pair and get them to store my bit of information. And I find that really fascinating.
So how did you get hold of the 6977s, and what was their typical traditional usage?
So I'll see if I'll show you where I got them from, actually. I'm going to step off camera here for a second as I reach around.
It's also going to be cool because you're going to see when there's a bit stored in that.
Yeah,
right?
Yeah, that was
I liked about it.
That's nice. Like you get a visual indicator of the memory as well.
Yeah, so there was an auction on eBay in Germany somewhere, and they had somebody came across a box of these. This was just some kind of indicator board that had, we'll see if it's got a conformal coating on it, so it reflects light like crazy. But each one of these is a single 6977 VFD, and there's 2 rows of them. So there's 58 of them on this board.
That's like the world's coolest VU meter.
Yeah, it's kind of what it was. Yeah. So I bought 2 of these, and I haven't taken this one apart yet. But I went through and used a chemical to get rid of the conformal coating, and then desoldered and cut lines and pulled each individual VFD off. And those VFDs are now living in there. And
Wow.
yeah, that was one as well, right? The one that's right there in the center.
Yeah.
So
yeah.
that's where it was one of those things where like I was talking with people and we were trying to figure out what to do for the memory, and somebody posted that auction up, and I was like, well, that kind of seals it. I guess we're going to build the memory this way, because that's way too cool not to do.
So
Wow.
what came first, the desire to use a tube or the desire to build a computer using a retro technology, or did they both gel at the same time?
So we can blame Ben Eater for a lot of things, and so we can blame Ben Eater for this as well. It was kind of one of those things where like it was the beginning of the pandemic. I was starting to get into electronics, and we had an old Tektronix oscilloscope, a 545B, I think, that my uncle had for years. It had been left out to rot and destroy, and a mouse had made a home in it and destroyed most of the wiring. So it was like, and I didn't know better at the time. I mean, at the time I could have thrown some water at it and sold it on Craigslist for $100, but I kind of looked at it and went, "This is nobody's going to want this. It's mostly destroyed. It'll never work again." So I ripped it completely apart and took all the tubes out of it, thinking that we could maybe sell the tubes on. And then I went, I've done things in electronics before with transistors. I've done things with ICs, but I've always been scared of vacuum tubes because they often need 300 volts or 150 volts. And we've kind of established that I'm not the most intelligent or brightest person around, so I make dumb mistakes and often stick my fingers where they're not supposed to be, and so 300 volts would be a bad day. But I started reading about them, and I was like, okay, so the filament only uses 6 volts usually, sometimes 12, and maybe more depending on the type of tube you have, like the radios we were talking about where they've got mains coming in. Sometimes those have like 35 volt filaments or something like that. But the filament is, for the large majority of tubes, 6 volts or 12 volts. It's like, all right, that's pretty low. Could you use just 6 volts on the plate, or could you just use just 12 volts on the plate? It turns out you can. Like, it depends on what you want to do with it. If you need power out of it, if you need to drive some heavy load, then it's all trade-offs. Like if I'm driving a speaker, the more B+ I have going into my transformer, the more that transforms into current coming out of it. But I'm not driving a speaker. I'm just doing on and off, right? So I don't need a whole lot of current. I only need enough current to overcome the voltage divider going into the grid, which is for me 440,000 ohm, 440K between the plate and minus 12 volts. So we're talking microamps of current that I need to supply, which is totally fine at 24 volts. And I decided on 24 volts because that was a multiple of 6, which means I can run 4 tube heaters in series.
Yes.
Okay.
And so to get back to the bin eater problem, while I was doing that, I was also watching bin eater's SAP1 series. And I was like, well, I want to build that, but I don't want to build that, right? So I'm going to do it out of transistors. And I was like, transistors is still easy mode. Let's go with tubes. And then I got halfway into it and I was like, oh my God, what have I done? Well, I got to finish it now, you know?
Yeah, you do. We're all watching.
Yeah.
How'd you come up? I've seen in your videos you use a mill to make your PC boards. I know Ben does milling too, I believe.
I don't have a mill big enough for this kind of project.
Nah. How'd you end up with that, and what do you use for a CAD to drive the mill?
So the mill itself is actually an Accurite mill power. It's a Bridgeport Easy Track with an Accurite mill power CNC attachment on it.
Okay.
It's a mill power 1, which you can't even find documentation for anymore. It's like we're talking the retro computing channels could look inside of that and do a video on our still in active use CNC thing. But in the world of CNC, I guess it's pretty new. The reason that I ended up milling my own PCBs is because I was hitting a point where I needed to start getting PCBs, and it was bad timing. I had ordered a PCB from a manufacturer in China, not the 2 big ones that we know now. It was a different one. It was Seed Studio Fusion or whatever. It was just whichever one popped up on Google that day. And I had ordered it right at the beginning of Chinese New Year. So like 2 weeks go by and they haven't even started production on my PCB. And I'm like, you know what? I'm done waiting. And so I canceled the order and I instead ordered some blank PCB materials, some raw PCB materials. So essentially single-sided stuff like this from a company that was here in America, because I was like, China's still on Chinese New Year's, so I want it immediately because I'm impatient. So I ordered some stock. It's just single-sided stuff. And it showed up and I started reading about how to machine and mill PCBs. And it took me about 15 to 20 failed experiments before I figured out all the settings that I needed to get right. And I use really wide PCB traces. My traces are 1 millimeter wide. And I use a grid spacing of 2.5 millimeters. So not only can I not run traces in between pins on like an IC, the trace would be too thick anyways. It would touch the traces, or it would touch the through holes. But it doesn't matter because obviously the thing that takes up the most amount of space are going to be the tubes on top, and the fact that I'm using nothing but through hole components. And then I use little jumpers. I don't know if you can see them. There's a bunch of jumpers right here along the top. So I just bend up little chunks of wire to make jumpers that allow me to jumper over traces on the bottom side that you can't see.
Here we go. Yeah.
And my camera is still
That's
incredibly focused on my beard, but we can see if we can.
No, I can see the jumpers. There's just a lot of light, and that's a good angle. Look at that.
There we go. Yeah. So there's a bunch of jumpers on there that allow me to jumper over traces. But what takes up the most amount of space?
Done back in the day, like In fact, you can still find some of the most mass-produced consumer electronic devices still have single-sided phenolic.
It's cheap.
PCB.
It's real cheap.
And the reason they use that is you can stamp it. You can stamp the boards. They heat them to 70 degrees C and stamp it with a press to cut it out. They don't use a mill or anything expensive. And a lot of particularly power supplies. The cheap switching power supplies you get, still single-sided with the occasional jumper here or there. And they have these, you check on YouTube, there's beautiful videos of Juki jumper insertion machines. It's like a giant sewing machine. It's
I wish I had one of those because I do it all by hand. bend it, snip it, bend it, snip it. It takes forever.
And the CAD tools, PCB CAD tools, there's no way of this still to this day. They won't. The developers are like, no one uses jumpers. It's like consumer electronics producers still do, but whatever.
Yeah. So to answer Bill's question earlier
Yep.
about what CAD tools that I use, I just use free software. So I make all the PCBs in DesignSpark PCB because that was the first one I tried, and that was the one I got used to.
That's a
And
British
then-
program. It's based on Number One Systems. I think OEM'd it to them
Okay.
because RS Components
Yeah.
is a British company, so they partnered with their local CAD
Getting a little
company.
representation going on in there. All right.
Westdev, actually. Westdev. The same ones that do Pulsonics and Easy PC and a few others. Yeah.
Okay. Yeah, but so you can make PCBs in pretty much any EDA software. And then once you get the Gerber files, so the Gerber files is normally what you send off to the PCB house
Right.
to produce your PCB. I use a program called FlatCam to pull the Gerber file
yes.
in, and it generates a G-code.
Okay.
And then I just put the
I've played
G-code
with
on a
FlatCam.
little compact flash, pop that into our machine, and hit go, and then I walk away, which is good because these guys here, because the density of the tubes on this one was so intense, I have to use really long PCBs in one cut because you can see on the processor I have a bunch of smaller PCBs with like connectors that go between them. So everything's kind of like in a module. So I can pull one module out, make a change, and put a different module in or something like that. But for the memory, I needed so many tubes in such a tight space that I couldn't do that. So the PCB itself is like 470 millimeters long or 480 millimeters long. It's huge.
Right.
For reference, the standard size that most PCB manufacturers will quote you for is 100 millimeters. So if you get up to 200 millimeters, that's getting big and getting expensive in a PCB house. And I'm up to near 500 millimeters on one of these. So like one of these through a PCB house would cost hundreds of dollars.
Yeah. Yeah.
But because I've got like a full-on Bridgeport Easy Track that has about 800 or 900 millimeters of horizontal travel, I can slice one of those up. But it's not fast. So it takes about 5 to 6 hours to cut one of those big PCBs.
Yeah, especially because the problem with milling, especially with your design, because you're only running everything at 24, you don't need to worry too much about clearance. So that saves a lot of time. I've considered milling preamp boards for tubes, and I've put those projects in my mind on the back burner because of that very reason. You have to configure your cam to cut away all unnecessary copper because you're dealing with high voltages.
Yeah. If you've got like 300, you don't really have to worry about arcing too much. But there's some people out there that've got 600 plus or 800 volts on their
especially
amps.
power amps. And if you want to go with a Fender based kind of concept, they were always up. Some of the voltages can easily get over 600.
Yeah, and at that point to point is the correct solution there, because you don't
I'm
have
just
to worry
going to
about
build
arcing as
one
much of
for
those.
myself. I'll do it the old school way. You can still buy all the solder eyelets and stuff.
So the spindle speed on our mill, Chris, because it's a Bridgeport Easy Track and it's meant for like cutting
Wood, metal.
Yeah, it's meant for like machining aluminum. The spindle speed's real slow. It's 3,000 max RPM. I run it at 2,800 RPM. It just means that I have to my feed speeds are really slow. And 27 to 2,800, Chris. I would be concerned about it if I had to babysit it. But I just hit go and then I go inside and play video games or something. Right? It's
Go pet the bunny. Yeah.
Yeah, it's very much so a fire and forget thing.
I like this comment. Yeah. Some of them are very dodgy.
Yeah.
I must agree. I've taken to doing some amp repairs for a local shop, which I don't know why I agreed to do it. It's so hard and it doesn't pay enough. But it's because I'm enamored with tubes, right? But anyway, you look at the old ones, everything's point to point and every wire is actually coated in fiberglass spaghetti. The way they used to do things with some issues like the grounding through the capacitor and your two-prong cable were super hairy. and then other aspects of it are like this thing is bulletproof. The tubes are the only thing that won't last forever in it. It's kind of crazy like that. I prefer boards, and I like to use slots for improved. If I'm doing anything high voltage, I will put slots in the board and cutouts to improve creepage.
Yeah, you see that a lot on old CRT boards.
And even current generation power supplies. If you want to get your power supply smaller, you're going to have to cut slots in it under the isolation transformer. It's just how it goes. So yeah.
Power when you get to power supply design is a very interesting field. For this, I'm just using I tried to stay period correct for 1955 for everything except the power supply. For the power supply, I'm just using a Meanwell, like a simple switching.
Yeah, and good on you. I would do the same. There's no need to have a 2 kilowatt EI core transformer sitting on your floor that you're going to hit your
150 kilograms of transformer cracking the concrete.
Apart from the cost, I mean, you can still buy. Of course, you can still. There's serious applications for 60 cycle transformers, 50 hertz transformers. You can still buy them, but it's just horrendously expensive. All that iron. Yeah.
It's not like they have them at Radio Shack anymore.
So
be able to run out at lunch and get a transformer.
Yeah. It's surprisingly hard to find a good tube transformer.
Yeah.
It is. Yeah. And you're going to pay. There are makers for them for the boutique audio sort of hi-fi, and companies like Hammond in Canada make them. There's one in LA area called, I don't know if Triodes from LA. There's one called Triad Magnetics.
Yeah.
There's another one. That might be the one in LA I'm thinking of.
I'm not sure where they're located, but they do come up a lot when you're looking for specific types of transformers.
And a power transformer that if you want this stuff, I recommend going to ham swap meets and not even eBay, because shipping kills everything now.
Oh yeah.
If it's got any weight to it or size, I feel like sometimes I have a friend who owns some FedEx routes, and his business is crazy. It just keeps expanding and expanding. And I'm thinking, I'm in the wrong business. Like, if I had a truck, these shipping companies make a lot of money. I think that's where all the money's going.
Yeah. Well, that and cardboard boxes.
Yeah.
So cool.
Can you give us a demo?
Yeah. We'll kick it on. So the memory is not going to be demonstrated because it requires like a bunch of jumper cables to connect the processor up to the memory. I need to make a new harness and a new remote control here. So this remote control only has 4 buttons or 4 toggle switches here for the instruction. And then I have 1 toggle switch here for forcing the data line on or off. Now it's so bright in here that I don't know if you're going to be able to see any of the VFDs. But if I turn those four up, these 4 VFDs have lit up down here, and I can turn them off. Let's see if we keep that light off. Maybe you can see that a little bit.
It's hard to tell.
Yeah, it's hard to tell. That's either I'm going to be extremely dark and you guys are going to be able to see what's going on, or it's going to be extremely light and you're not going to be able to see what's going on. Let me turn off the overhead lights right quick. That might help right quick. All right.
It's still pretty bright in there, but
it's because I'm still trying to finish building the room here, and I haven't bought blinds yet. So the windows are just open. Let's see here. I think I can get this a little closer now.
Oh yeah.
So if I turn those on, I think you can maybe just barely see the lights flipping on and off there.
Yeah.
All right.
We can see that.
Okay, so The processor itself has got to do a bunch of stuff, but the important things to notice is that this is the data bus here, and you can see that the top one on the top left here illuminates whenever I'm forcing the data bus.
Yep.
So this is an indication of what's on our data bus. And then we have the result register and the write signal next to it. I might have those transposed, but we'll find out here in a minute. So I've got to initialize the processor, which means I need to turn the input enable register on and the output enable register on. So we do that with a 1010 operation. We'll force the data bus to 1, and then I'll push the clock. And I can see the input enable register is turned to on. And then we'll do the same with the output enable register. It's kicked on. And then we want to make sure that the result register and the carry register are both at 0 before we start any operations. So 0100 forces the carry register to 0 and forces the result register to 1. So if we run that one right quick, we know that we get a 1 in the result register, and then we'll just load a 0 into the result register. So you saw that the second LED, the second VFD here, when it's on, that's telling me the value of the result register. So right now the result register has a 1. Now the result register has a 0. All right. So now everything's initialized. The result register is at 0. The carry register is at 0. We can get input into the system. We can get output out of the system. So for example, if I want to store a 1 in memory, I'll load, which is 001, a 1 into the result register. So the result register is now storing a 1. So now I want to get this 1 somewhere. So I'll do a store operation, which is 1000, and this outputs whatever's in the result register onto the data bus and kicks off the write signal. So when I push the clock here, we're going to see the data bus, which is top left here, illuminate, and we're going to see the write signal illuminate as well. So you can see that the top 3 now are all illuminated.
Okay. Could you cup your hand around the right side of that? So
trying to block some of the...
Yeah, or just cast a shadow.
Let me stand on this side here. Maybe that'll help.
Yeah, it's a little more obvious.
Okay.
Yeah. Yep.
Yeah,
That's cool.
It's the camera freaking out because I can see it clear as day in here.
Yeah.
So when I'm pushing the clock down, I'm holding it down. So on the bottom right here, this is telling me what my clock is.
Okay.
So we've got the value in the result register being put onto the data bus. The data bus now has a 1 on it, and we've got the write signal going on. So the write signal is actually going to tell the memory to store whatever is on the data bus at the address that is currently being asserted to it. But I don't have my extra 6 switches over here for the address, so the memory can't store anything at the moment. And that was kind of what I was experimenting with in the last episode. Was I was using actual jumper wires on the memory itself to set the address.
Gotcha. Yeah.
So that's how I get a bit into memory. So right now we have a 1 in the result register. If I want to add that with something, I can put a 1 on the data bus. So 1 plus 1 equals 2. 2 in binary is 1, 0.
Yep.
And then if I do a 0010, I think that's right. It's been a while since I've looked at the thing. It's going to do an addition. So our result register is going to go to 0, and our carry register is going to go to 1. Now, I don't have the carry register indicated on here because the carry register never leaves the processor. The carry register always just stays up here internally. But we should see the result register kick off. And yeah, the result register kicked off. So we did a successful addition there. And then I can do a store operation to store that 0 someplace in memory. And then if I want to drop the value that's in the carry register into the result register, I just do an addition of 0 because 1 plus 0 equals 1. So that's going to drop the value of the carry register into the result register, which illuminates our result register again right here. So that's kind of how we can move data around the system and do stuff with it. So surprisingly,
That's
that all
beautiful.
still functions correctly.
That is a beautiful thing. It's a cool question here. Someone's asking, what literature or books or sites would you also recommend to dive into this stuff? You've already mentioned Ben Eder. We all know he's a genius at explaining these concepts, but then were there any other...
Ooh, I need lights again.
Any other wells of information that you draw from in your quest?
So Ben Eder is fantastic for edutainment. He did an amazing job of presenting educational material in an entertaining manner.
Yes.
But if you're looking for like proper hardcore getting into how vacuum tubes first of all function and how they're used in computing situations, my holy grail, my holy Bible is the IBM 604 Customer Engineering Manual.
Oh,
it's on BitSavers. If you just go to BitSavers,
I love that place. Yes,
yeah, BitSavers is fantastic.
It's one of my favorite places.
What I do is I go to Wikipedia and I look up vacuum tube computers, and then I go to BitSavers to find the documentation on that computer. And so, kick that on. Maybe that'll get a little more light on me. So the 604 Customer Engineering Manual is pretty much my holy grail. Anytime I have a question for something that I don't understand, I go to that. And they do an excellent job in that manual of starting with what's a vacuum tube, how does a vacuum tube work, where they show a similar drawing to that one that you showed earlier of the actual emission. And then they go into what the different grids do and stuff like that. And then it goes into how to build actual computing circuits using tubes.
So this is one of my favorites, Theory and Applications. This is like the OG Bible of electron tubes. Got this, I don't know, some years ago from, I probably eBayed it actually. I have to be careful with the pages because they're kind of, they're yellowed and brittle now.
Fall out. Yeah.
But this covers everything from all the different types of tubes, their basic theory of operation, all the way to different applications. That's what I like about it, is the applications side, because it talks about, like, this whole chapters on all the different kinds of oscillators, all the different kinds of flip-flops and digital circuitry, different classes of amplifiers, grid deflection amplifiers for tubes, like for, when I say that, I mean either oscilloscopes or televisions, everything's in there. It's old enough that it probably, I think this edition of this is old enough it doesn't cover color TV technology, but
CRTs are like a whole, man, that's a whole different game. I mean, they are still technically vacuum tubes, but boy,
yeah,
it sure does get weird.
Yeah.
And if you want to talk, I'll show this off. I haven't used it yet, but if you want to talk about really strange vacuum tubes, this is probably the weirdest vacuum tube that I have.
That is cool. What on earth is it? It looks like some kind of gun.
It's the best prop for a sci-fi TV show. It's called a photo multiplier tube.
Oh, right. That's the input to a camera, right?
To a photo detector, yeah.
Yeah, this is the idea is that this one detects extremely small traces of, I believe, blue light. So a blue photon will come in the front here, and it'll go through these. You can kind of see they have what look like cylinders. Everything's super reflective, but it looks like a bunch of cylinders in there. And essentially, it's like a cascading electron amplifier, essentially.
Right.
So a photon will strike one, and that'll knock off some electrons that then get directed into the next one, which knock off a few more. And it goes back and forth, knocking off more and more and more and more and more until it gets to the end where it's been amplified 100,000 times or 200,000 times or some huge number. So you use highly specialized tubes like this to detect photons of light. Yeah, it's crazy.
It is.
Well, those are some of the things where tubes are still manufactured, I think, for medical applications and whatnot. Or am I off on? I'm just guessing, right?
Yeah, well, I don't know. I don't really read about new stuff, but there are still a lot of vacuum tubes in use today.
Well, radio
stuff,
transmission as well. For high power radio transmission, there's still
it's hard to beat like a klystron or something like that, you know.
Right.
They get real, or traveling wave tubes. Traveling wave tubes are also very fascinating. There's just a lot of things, especially when you get to extremely high voltages, that semiconductors can't do. Interestingly, one of the things they talk about in the IBM 604 manual, even though we're not talking about high voltage or transmission anymore, is that they talk about how silicon diodes have some reverse leakage, whereas a vacuum diode does not.
Right.
When a vacuum diode cuts off, it is cut off. Nothing can go backwards up until the point that you arc it. At which point you've got so much voltage that everything has broken anyway.
Yeah, right.
But if you're dealing with like extremely sensitive signals, and you need that cutoff to be 100% off, a vacuum diode is the correct answer there. And for IBM, when they were designing their initial circuits, they talked about germanium diodes, and they said we use germanium diodes, but we only use them in areas where space is of the most importance. In other places, we use the 6A05 or vacuum diodes because they have better properties for what we're doing. And so I find it interesting that we've done, even today, we've done massive miniaturization, but there's still some scenarios where you just need a vacuum that you can throw electrons through.
Yeah.
Well said. So excellent. Well, if we look at the time, it's been an hour and 15 minutes, and talking about tubes. This was very cool.
Very indeed.
Yeah. So thank you for coming on again, and
thanks for having me
about this really cool topic. So for people that don't know, they could Google Usagi Electric and find your YouTube channel, I'm assuming. I also posted it in the comments. And also you can find our YouTube channel by going to Coriolis-effect.com. And there's a link to our Discord there as well. So
yep. And what's your YouTube channel address? I'll put it up on a banner real quick.
YouTube has this new thing. Tag. Tag thing. So if you just do @Usagi Electric, it'll bring me up. YouTube.com/@Usagi Electric.
Yeah.
Let's see if we can get this scrolling thing, new technology.
Yeah. New old technology.
Hey, there we go.
Did I spell it right?
Yep. You can think of it as United States of America government issue.
That's good.
It's the easiest way to remember it.
My tokenizer came up with Unagi Electric, and that'd be like Eel Electric.
Yeah, Eel
like
Electric. There's a thread we can create there.
Yeah.
Yeah, Usagi is just Japanese for rabbit. That's the logo. Usagi Electric, a little bunny.
Yes.
Yeah.
I try to have a video of bunny at the end of every episode. Although we've got some cats, so every once in a while they sneak in as well. But Usagi is for bunny, so Bunny Electric.
Very nice.
Very cool. Well, I want to thank you both for being here. And next, I don't know what we'll do next week, but we'll figure out something in the coming weeks. Let's say that, and find something else to talk about. That's cool.
Getting back into the swing of it as the new year progresses. Trying to finish projects, and there's a lot of interesting things out there. A lot of other people I'd like to see if I could get in touch with and have on as guests as well. So we'll see how we go with that. It's always...
Well, if you ever need a warm body to fill a seat, give me a ring.
Yeah. Well, we really appreciate you, David, and what you're doing is amazing. Like,
thank you.
Got a lot of fans now. So, I mean, keep it up. It's very, very cool.
Well, in 2023 is the year of the rabbit, right? So on the Chinese zodiac. So it's my year. It's the year of the rabbit.
It is.
Cool. All right. Excellent. Okay. We'll catch everyone later.
Okay.